open vocabulary 3D object detection. So have any of you guys heard of this framework called open vocabulary before? No? Okay, that's good. Well, this is kind of what Professor said, the direction that 3D object detection is taking. And what I'll do this lecture is kind of go over two main things. Kind of what is this idea of open vocabulary? And to begin, we'll start with the context of 2D object detection, and then how we can apply this for the 3D case with regards to autonomous driving. So I like to start with kind of the history of what object detection kind of have looked like. So before 2012, a lot of these object detection algorithms were very classical, meaning they didn't involve deep learning. But within the last 10 years or so, deep learning has kind of taken over this space. And a lot of these methods you've seen in class, we start with anchor-based methods and anchor-free methods like CenterNet and CornerNet. And you can see that there's just a lot of work in this area, right? But as noted, these methods all follow kind of this idea of being supervised completely. So the idea is that if you want to train a detector, right, you're going to show it what it needs to learn, and you expect it to be really good at what it does. For example, if you're training an object detector on cats and dogs, during test time, you're going to expect that your results perform well, and because that what you've seen during training is what you're going to get during test time. Well, one issue with this type of thinking is that even though your performance on what you expect might be well, you know that this method's not going to generalize to classes that you haven't seen in your training data. So, so supervised methods generally work really well on labeled data, like within kind of this small distribution of classes. For example, like we usually expect when we train that we're going to use between 10 to 100 classes. But if you think about like the process of adding more classes and improving generalization, it's kind of expensive because not only do you have to mine and label more data, which is cost effective, which is costly, but you also have to think about your model architecture. Adding more classes requires you to change it and then retrain as well. So the question presents itself, is it possible to perform object detection on unseen data and do it well? And if so, what does it look like? So this concept is called zero-shot learning, where you can kind of see that. Suppose we have a detector that only trains on dogs. During test time, we may also want it or expect it to be able to kind of generalize and potentially detect other animals like cats, right? Which is considered novel because we haven't seen it during training. Of course, it's also going to perform well on dogs because that's part of our training data, but we also want to generalize to classes not seen in training data. And just a thought right away, this task is kind of daunting and it seems pretty challenging, but there's kind of a lot of works recently to go towards this trend. So revisiting our supervised case, how you perform the classification is you first start with an image. Here we have an image of someone getting mauled by cheetahs. Well, he seems to be enjoying it. And then so what happens is you take an image and you feed it through a vision backbone, and what that does, it will extract the features in which you feed to potentially some region proposal network, and that will produce object proposals. And these object proposals usually encapsulate or encode latent information about where objects are and what the class is. For example, one of these features may correspond to this human, and it will tell you where precisely the corners are of the bounding box and what the fact that it's a human, right? So to classify, we take in class, what we do is we take class weights, and we perform a dot product to compute class logits. And what happens is you perform the softmax and you take the highest value, and that becomes your class, right? So in this case, you can see that this jaguar or this cheetah, sorry, corresponds to the second embedding because it has a high activation for the cheetah classification weights, right? Now in zero-shot learning, a couple changes happen. The first being we replace the classification weights learned during training with a text encoder that's frozen, meaning we don't touch it when we train. And this text encoder can come from language models or vision language models. And what happens is essentially you give the classes, and the text encoder produces what's called word embeddings. And these word embeddings can sort of act as class weights. And then on top of that, we add a projection layer. And what this projection layer does is it maps the object features into what I call the object text aligned embedding feature. Um, so a bit more about this later, but at a high level, what you notice is that if you take the dot product of two similar vectors, the value will be high, which kind of measures the similarity, right? You can think about that with the cosine similarity measurement between two vectors. So, so instead of training classifier weights, we simply use word embeddings to classify jaguars, right? So this idea is kind of similar to a popular zero-shot classification model called CLIP, produced by OpenAI. And CLIP is actually trained on a massive amounts of image text pairs, right? So there's two components to it. The first is the image encoder, which takes images and produces image embeddings, and the text encoder, which takes text and produces text embeddings. So the idea is you want to map these image and text into a shared vision language embedding space. And they can do that during training by performing what's called contrastive learning. So I'm not going to go into detail about that, but the idea is that um, image and text that are closely related are going to map to the same embedding space or close and be closer in that space. And things that are not similar are going to be more spread apart. And to kind of classify using CLIP, like I said before, we just use the cosine similarity. So up until now, does that make sense? Yeah, feel free to interrupt at any point. So one assumption we make when we use zero-shot learning and we take these text encoders is that the text encoder has learned a good representation for each class in the embedding space. So like what I mentioned before is that, for example, person in the embedding space is probably has a significant distance compared to things like giraffes, lions, and elephants. But you can see like something like a lion and a cheetah may be close in the embedding space. And what contrastive learning does is it kind of enforces this relationship. Yeah. So the question now is, I mentioned that there was a projection layer, a vision to text projection layer, right? So the idea is you want to take your object features and map them to the same space where it's aligned with text. Now that's that's another challenge in itself, but let's take a look at how we do it. So, like I mentioned before, we start with the image itself. We produce the object features, right? And I mentioned that these encode the image, the object region, as well as the class. So we can actually decode the information from the object proposals and extract the region of the object. Then what we do is we take the image encoder from clip and we produce sort of our target alignment embeddings. Like, and the goal is that we want to align or make them equal the projected the text and line embeddings and the target, right? And what we can do is during training we can add an alignment loss. Typically, you can just use like a similarity loss or a L1 loss. And what that does is it forces this vision to text projection layer to produce text aligned features from object proposals. So the reason why we use clip image encoder is because the images are more kind of representative of what objects can be. So it's probably easier to align that way. But it's also fair to say that like implicitly, when we're aligning to these image features, we're implicitly aligning to text because the clip image encoder is also aligned with text, right? So now we have features that are text aligned, and we can do the dot product similarity with word embeddings to classify them. So in a zero shot setting, I mentioned before that the classes we train on are not necessarily the classes that we see during test time, and even during deployment, potentially you see way more classes. So that's something I note here. So the question is, if we train a strong vision to text linear projection layer and it performs well on base classes, do we expect that this will work for novel and unseen classes? So here on the right, you can see that maybe the distribution of this data from the training differs significantly from the test. So the question is, if we train on this, will we be able to perform object detection on the test set? And this is assumption we make when we do these type of methods, but there's no evidence that this will work. And we often see this, that this is not the case that it will work because there's significant drop off in performance with unseen test data. So that's where open vocabulary object detection comes in. So this type of framework tries to kind of bridge the gap between trained data and test data. And essentially how it does this is by leveraging large scale data, large scale image to text pairs, kind of what you see with VLMs. They're trained on massive amounts of data. And because of that, we have kind of enhanced generalization. And because of that, we will improve with our zero shot performance. So when we talk about training on large scale data, what methods do is they combine kind of multiple sources of image to text pairs. So the most traditional case would be just object detection datasets, where your image would just be the region of your object cropped from the image, and your text would be the class name, right? So that's easy to use. The next one is this idea of phrase grounding datasets, and what this data involves is this task typically traditionally is an image given with region crops, and it's paired with a phrase um, that where there's nouns in the phrase that match different regions. And this task is to take these phrases and dissect them into different objects and match the regions to the objects. So naturally, like this task is hard by itself, but we can actually leverage this for object detection. And lastly, there's a popular trend of using web crawled or web scrape data. And because the benefits of this is that there's a lot, but unfortunately, we don't get the specific annotations of which regions associate to which object. In addition, the samples from these data sets are really noisy, so uh, there's a lot of work to try to filter out the noise or potentially see what's useful. So because there's no specific region paired with each words in the phrase for web crawl data, a lot of methods actually pseudo-label. And what does that look like? So let me get my pen out. So here we go. So suppose we have this image text pair that we scraped from the internet, and somehow we found a phrase that pairs with this: a geese wearing sunglasses on a sun chair at the University of Waterloo. What methods will do is first they'll extract the nouns from the phrase, so geese, sunglasses, sun chair, and University of Waterloo, and then they'll feed it into a previous teacher or past method for open vocabulary object detection. Um, and they'll kind of come up with proposals for these objects based on the nouns, right? And we can expect these to be noisy because um, because of the nature of like the data, right? So what ends up happening is they have to come up with additional methods to filter out noise aspects, and one simple way to do that is to feed these image crops to clip and see if they have a high activation. So that's how they pseudo label the web crawl data and use it for training for open vocabulary methods. So once they do that, uh, you're able to achieve pretty strong performance or impressive performance for zero-shot performance. For example, here are a bunch of images of YOLO World, a popular open vocabulary detector, on the ELVIS dataset, which is deemed pretty challenging. And the model has never seen any of this data before, but it shows pretty strong performance generalizing to these concepts that are tested at during this data set. Yeah, so the idea is that, just to summarize, we don't really like specify what we're learning during training time, but we train on a lot of data so that we're able to generalize and kind of have this zero-shot performance. So I kind of just gave like a high-level insight to this methods, but there's actually a lot of work that goes into this particular niche of work. So feel free to check out some of these resources if you're interested. This is for 2D open vocabulary detection. So aside from that, uh, my work in research and kind of what I've been studying during my graduate studies is focused on open vocabulary for autonomous driving. And in that sense, it's no longer a 2D problem, but it becomes a 3D problem. So I'd like to share kind of the project that I've been working on for the last year or so. And the name's not really important, but let's take a look. So the first question I have is, what would it take to have a similar framework in the 3D setting. For one, in autonomous driving, our sensory inputs are no longer just images. It's actually usually images and LiDAR point clouds. So what this means is we actually need to have them in 3D, which means replacing the 2D bounding box with 3D bounding boxes. So it's actually not too different. If you can think about it at a high level, now we're just having two backbones, one for images and one for LiDAR point clouds. And then I abstracted this a little bit, but there's going to be a layer to fuse both these modalities and produce a feature for the 3D object proposal network. And this is the same thing as, not quite the same thing, but it serves the same purpose in the fact that these proposals will tell you where the objects are in 3D as well as their class. And we perform the same steps. We take a projection layer that projects vision into text, and then we perform the same zero-shot classification. So the only things that really changed are the way we process the sensory inputs, but the training is quite the same, and the way we do classification is the same. Now, even though I said that a lot of this transfer from 2D domain to 3D domain is the same, there's one main issue that hinders this. So the main problem is data, in fact. So in 2D, we know that there's large scale data, and we have access to a lot of different classes, and we can learn a very good general representation in our object detectors. But in the 3D case, we have kind of like we have limited data, right? In 2D, we have million images per data sets with rich captions, descriptive labels. But unfortunately, in 3D, each data set may have thousands of data sets with only maybe a dozen or so classes. And an example of that is the Kitty and dataset, the Kitty and Waymo dataset, which are popular autonomous driving datasets. And each of these only evaluate on 3 classes. So in Waymo, it's vehicle, pedestrian, cyclist, and in Kitty, it's car, pedestrian, cyclist. So that begs the question, right? What if we want to detect things outside of these classes? And even if we do, right, we want to classify these at a higher, or actually, this is an error. We want to classify at a semantic level that's more meaningful than just car and vehicle, right? So a typical case that I outline is like, for example, even if we can detect something on the road as a vehicle, it matters whether it's a school bus, a fire truck, or an ambulance or a police vehicle. The way we respond to these different vehicles are different, right? So that's where the importance lies. So since we have a data problem, I want to know if there's a scalable solution to this problem. So suppose we can collect terabytes of driving data, and our goal is to generalize across a variety of object categories. Is there a way to provide 3D text pairs given an open set of categories without human labeling efforts, right? So you can imagine labeling terabytes of driving data is costly, and there's companies that spend a lot of money just to label these data, especially when you're just starting out. And so I propose this idea that given all these unlabeled data, if a user can just provide what it wants to label, in other words, an open set of classes, and we feed it to some auto labeling method, can we provide labels for different types of objects outside of just these standard car, pedestrian, and cyclist classes, right? So one way that the research industry is moving towards is to leverage vision language models to help particular and these specific tasks, such as object detection. And the main idea that we can do is leverage these VLMs to generate 3D bounding boxes. More specifically, because we have the multi-view RGB images associated with our driving data, can we use the 2D space? So something like open vocabulary object detector and segmentator to propose these 2D proposals in 2D. And then what we can do is take these and convert them into 3D boxes. So let's see how we go about doing this. So the first way to do this is the first step is to pair novel 2D proposals with their corresponding clusters in 3D. So I mentioned before, the first step is to get these 2D proposals. So when you pass them through a detector, open vocabulary detector and segmentator, what you're gonna get is bounding boxes in 2D, right? So these are your regions as well as the object mask, which is not really important for now, but it'll be used later. And what you want to do is associate them to the objects in 3D space. So you can start by taking the LiDAR point cloud and clustering the objects out. And then we take some association algorithm, and then we pair the corresponding regions with their point cloud. So what that leaves us is a bunch of cross-modal proposals. So you might be wondering, how do we associate these 2D proposals with their object clusters? Well, the easy way to do it is to take the 2D image and using the calibration between the two sensors, camera and LiDAR, you just project the 2D image into 3D as a frustum. And what you can do is just choose the most spatially relevant object cluster that matches the proposal. So in this case, we have this SUV, and when we project it into 3D, we see that this object cluster coincides with the center ray. And that's an easy way to tell that it's our object of interest. So after we do that, we don't want to just pair them. We also want to find a 3D bounding box that fits appropriately on this object cluster that we found. So the question begs, how will we convert a 2D bounding box to a 3D bounding box? So this is actually non-trivial, particularly when you think about it, because at longer ranges, point cloud becomes more sparse. In addition, when you're driving, a lot of times you deal with occlusions and only parts of an object is visible. But even though we only see part of it, part of an object, we still need to label the parts that we don't see, right? So let's look at how we can do that. So the first thing to recognize is that we can actually formulate this problem of finding box parameters as a continuous nonlinear optimization problem. So in our optimization problem, what we're trying to do is find the box parameters theta, which minimizes some cost function. And the cost function will take in things like it will take consideration of the object cluster points and then also the parameters of the 2D bounding box from the image. And in a bit, you'll see why. But in addition to that, we can also simplify the optimization process by providing anchor boxes. And the anchor boxes will kind of fix some of the parameters and make sure that your boxes are searching in a confined space. Without this, you can imagine that an unconstrained length, width, and height search will be pretty challenging to solve. So how do we parameterize the loss function, or what terms do we take into consideration? Earlier methods propose we find these parameters by considering two main costs. The first being point density cost. And this is simply just the percentage of cluster points outside of the 3D bounding box. So here you can see in a potential pseudo label, there are object points that are slightly outside, but for the most part, the object is well labeled. Because we want all the points to be inside the pseudo label, what this loss or what this cost term will do is penalize the fact that there's a surface that is kind of leaking out of the bounding box, and you'll accumulate some loss because of it. The second term we can look at is multi-view alignment. So what that means is when you reproject the 3D box back into 2D, because you have the calibration, we expect that the dimensions of the reprojected box are going to match the 2D proposal from the VLM. And one easy way to measure the misalignment is IOU. So you can see that the reprojected box here is slightly off. And because of that, you might accumulate some loss. So what this term indirectly does is not only does it force the box to be tighter, but you kind of get some orientation cues from this term, right? While just having these two loss functions work well, we find that it's still prone to some common mistakes, namely poor L-shape fitting, where the pseudo label algorithm fails to identify that we want like a proper L shape, and just because you have all the points within the box doesn't mean it's sufficient enough. And then also misinterpreted surfaces. So suppose you're looking at this car from the left and you can only see the bumper, the front bumper, because of the field of view. We only have one observable surface. We should know that the surface of the bounding box that is closest to the ego should be biased towards these points. Or else you get a case like this where the front bumper becomes the back bumper. And then there's also some common misalignment issues where it's 90 degrees mislabeled. So why is this the case? Like I mentioned, the cost function previously mentioned does not consider L-shaped fit. And then we also need to add a bias towards box faces that are closest to the ego. So we kind of need some physics aware cost term. So it's what we can do is actually just extend the cost function to include these factors. That's pretty simple, straightforward. Now to solve the linear continuous optimization, we can use an algorithm that maybe some of you have heard of from your algorithms course, or not sure, but the particle swarm optimization solver. And what that does is it takes random initialized values, and then it takes multiple candidates, works together, and tries to find the bounding box parameters that are most optimal. And you can see that through kind of the solver, through many iterations, we can come up with a reasonable bounding box for our object cluster. So here's a video of taking 2D proposals from an open vocabulary object detector and providing 3D pseudo labels in which we can use for training. So what you're seeing is that the user or myself has asked the open vocabulary object detector to find different objects outside of just the regular three classes, and we try to label them, right? So stuff like, sorry, maybe stuff like traffic signs and garbage cans and whatnot, maybe not maybe excluded from labeling, but we show that if you just follow a labeling method like this, you're able to at least try to produce bounding boxes, right? And not sure why it's not showing. Oh, here we go. Yeah, and these boxes are noisy compared to if a human labeled them, but in general, I think this is a good step towards uh, kind of these unsupervised methods. Or so after we have these, we accumulate all our pseudo labels, we can actually proceed to training. So what does that look like? Of course, like when you produce your 3D proposals, we also need to have a regression head for the boxes themselves, just to figure out localized objects and provide a shape. But we can actually break them up into two different problems, uh, one being box regression and the other being this alignment problem, which comes with classification. So to supervise over the data set that we just labeled, what we can do is we can supervise the box regression with the box losses, which is pretty straightforward. We take the boxes that we labeled, and then we we supervise things like the location and the parameters of the box, and that will allow us to have high recall for objects that we care about. But on the other hand, we also need to perform some alignment between the 3D object text alignment embeddings and what we propose as the target alignment embeddings, which is also produced by CLIP. And we get these CLIP embeddings by retrieving the region crops produced by the vision language model. And because we know we're able to pair and associate them ahead of time, we can just easily retrieve them and perform this alignment. So I mentioned how we can train, but during training, there's one issue that is often overlooked. It's the fact that sometimes alignment can be actually noisy. So one case of this is which I called inclusion-induced noise, and this occurs when the object of interest um, in the clip embedding, or no, the object of interest is corrupted by another object uh, driving by. For example, like our object of interest in this image is the truck, but we have someone on a motorcycle passing through, and at the time of detection, when we pass it through clip, the feature produced that we're trying to align to becomes ambiguous. Clip kind of struggles because it's thinking, is this a motorcycle? Is this a pedestrian? Or is this a truck? You can see that these three classes have a strong similarity to the image embedding, and because of this, it produces sort of ambiguous targets, right? The second one, the second source of noise is resolution-induced noise, and this occurs when the object of interest, uh, the object of interest region crop is insufficient in resolution, and as a result, the clip embedding becomes ambiguous as well, right? So you can imagine that as your image crops becomes smaller, it becomes harder to distinguish between different classes. So how do we address this? So the idea I propose is that if we can identify these cases ahead of time, we can actually prevent them from affecting our alignment training. In other words, we can flag these cases, and then we just do not we have them not contributing to the alignment loss. Well, it's also important to note that the boxes associated with these object crops are still used uh, during the box regression loss, so that the recall is maintained. So for example, it might look like this when we're filtering out resolution-induced noise. The pedestrian that I showed previously may only occupy a few pixels, and we can threshold the amount of pixels we choose for that we require for our training. And a car with a higher resolution is fine. For occlusion-induced noise, we can use the segmentation mask that we got through our open vocabulary segmentator, and we can use it to estimate the occupancy. And then we can threshold by minimum occupancy, which is going to be just simply the percentage of the pixels occupied by the image crop. You can see that in this case, we have a van or a truck, sorry. Our segmentation mask tells us that this object takes up a significant portion of the pixels in the image crop, and we can label it fully observable. Whereas on the other hand, in this case, there's a flatbed truck, and it's clearly occluded by another vehicle, and because of this, we're able to identify that's heavily occluded. So as a result of these two methods, or these two filters, we can actually improve our alignment. And basically, we show that filtering out these poor alignment samples actually improves our classification performance on the test set. So at test time, I mentioned before that we can actually use different novel classes. And that's where the part of using kind of high specific classes. So instead of car, we would use like sedan, pickup truck, and SUVs. And we can actually use those class for classification and perform kind of classification at a more semantically rich level. So if we put everything together, we're able to train an open vocabulary object detector in 3D. And the key thing to highlight is that we actually don't need any human labels to achieve decent performance. You can see that here I compared to previous methods. We're able to achieve better results and something closer to our ground truth target. In previous methods, things that are often overlooked are larger objects at different distances and rare objects at larger distances, but our method's able to kind of supplement and learn these cases. And then I talked about being able to discriminate between classes at a fine grain level. So before, in traditional object detection, we might label all of these as cars. But now we're able to distinguish that, yes, this is a pickup truck and this is a sedan and this is a SUV. In this case, we're able to also tell that this is not just any construction vehicle, it's an excavator, as well as the people working, because they have helmets and they're working in a construction zone. We can call them construction workers. And yeah, here are some more examples. Previously, we would have called this just a bus, as well as over here, but now we can discriminate them and say, yes, this is a double-decker bus and this is a transit bus. Yeah, and so if you're interested in this field of research, I've actually listed some introduction work that's pretty recent, and you can actually check this out if you're interested. But besides that, that's kind of it for my presentation. Thank you for listening.